Good morning. Today we're going to look at an example that's going to help you with the lab you're working on, the PPT lab. When you look at your PPT chart, you can see that the very first column is titled reactants. And so I'm going to use what I call station 7 as the example. You won't fill this in on your PPT chart. You should be doing this in your notes, but it's going to be very similar to what you'd be doing on your PPT chart. Now, when you look at the two bottles that I've got a bottle that says 0.1 molar NiNO3 as one of my reactants, and then my second reactant for station 7 is 0.15 molar, you can see it right on the bottle, Na2CO3. So when I write my reactants down on my what would be PPT chart, if I were doing station 7, I would write it down Na2CO3, and then my second reactant is NiNO3. Now, when I look at the chemical formula, it again reminds me the charges on my ions. Carbonate is a -2 charge, and I can tell that because it took 2 sodiums to balance it out. My nickel must be nickel plus 2 because it took 2 nitrates. In order for you to predict who the products are, you have to be able to identify what type of reaction it is. So of our choices, single replacement, double replacement, synthesis, decomposition, combustion, we're going to look at our reactants and see that we've got a cation anion reacting with a cation anion. So we're going to use we're going to predict that this double replacement reaction is going to form 2 different ionic compounds. Well, keeping in mind our products have to be cation anion, we're going to want to do T-charts to figure out which products we're going to form. Well, my sodium is a +1 charge, and that would then, my sodium from this compound is going to combine with the nitrate from that compound, nitrate being a -1, and it would go together 1 sodium to 1 nitrate. And so one of my products is going to be NaNO3. My second product, the nickel from the nickel 2 nitrate, is going to combine with a carbonate. And since nickel is a +2 and carbonate is a -2, it's going to go together 1 nickel with 1 carbonate. And my chemical formula for my second product would be NiCO3. As you look at the PPT chart, you see that the next column over asks you to write a balanced chemical equation. Well, I'm going to put my balanced chemical equation underneath this so that you can see how that would work. I'd have sodium carbonate, my first reactant, and leave enough space, reacts with nickel 2 nitrate to form sodium nitrate plus nickel 2 carbonate. Now, when I balance my equation, I've got to keep in mind that I've got, oh, you kind of can't see it here. I'm slid off the board. Let's see if I can zoom this a little bit here. You can barely see it. Okay, so we have to make sure that we're conserving mass here. We can't create nor destroy matter. It's just an ordinary chemical change. So I've got 2 sodiums on my reactant side. I need to have 2 sodiums on my product side. I do that by adding the coefficient of 2. I've got 1 carbonate in my reactant. I've got 1 carbonate in my product, so I'm good. I've got 1 nickel 2 in my reactant, 1 nickel 2 in the product, and now adding this coefficient 2 here, I have 2 nitrates on both sides. So this would be my balanced chemical equation. The next column over on your PPT chart asks you to do the overall ionic equation. Well, for us to do the overall ionic equation, we're going to need to refer to the solubility guidelines that you received. So I'm going to rewrite the balanced chemical equation so that 1, so you can see it, and 2, we're going to need it as our guide to figure out how we would lay out the overall ionic equation. So I've got I've got sodium carbonate with nickel 2 nitrate, and that formed sodium nitrate and nickel 2 carbonate. Now, the overall ionic equation, that's the balanced chemical equation. The overall ionic equation lets us think really more deeply about what's happening in the reaction. And what we're going to do is any of our compounds that are soluble in water, we're actually going to show them separated out or dissociated into their ions. So my sodium carbonate is clearly soluble. When you look in the bottle, you can see that it's a clear liquid in there. So we're going to represent that by dissociating or separating out our sodium and our carbonate ions. Since I have one sodium carbonate, that would separate into 2 sodium ions, and then you represent that it is dissolved in water as the solvent by putting that AQ after it. And for every 1 sodium carbonate, I have 2 sodiums and 1 carbonate. And you can just do the CO3 minus 2 with, again, the AQ after it. I'm now moving on to my second reactant, and in my second reactant, you can check the solubility guidelines, or you can look at the bottle because these are your reactants, and you can see, in fact, that nickel 2 nitrate is soluble. To confirm that, looking at your solubility guidelines, you can see that although nickel is not listed on the solubility guidelines, that it tells you that nitrates are soluble and there are no exceptions listed, so the nickel 2 nitrate would be soluble. That means it's going to break apart into the nickel plus 2 ion AQ, and then you're going to have 2 nitrates. We're now at our arrow because we've broken apart our reactants, and now we're ready to look at our products. Now, when I had written the balanced chemical equation on the previous screen, I had added the 2 coefficient there. When I transferred it to this page, I left off the 2. It's time that I add it. And I could tell that I needed to add it because I'm kind of looking ahead at what I'm going to do. I'm going to separate out this sodium nitrate. And I can see here for my reactants, I have 2 sodiums. All of a sudden, I was going to drag this, and I said, wait a minute, it looks like I destroyed matter. That reminded me to go back and add my 2 BCE. Okay, so now I'm going to look at my products. Now, my products I don't have yet. I haven't done the experiment yet. I haven't put the solutions yet in the well. So I'm going to need to see what's true about my products. So I head to the solubility guidelines, and the first product I'm going to look up is sodium nitrate. Well, when you look at the solubility guidelines, it tells you that alkali metal compounds are soluble unless, and there are no unlesses. So my sodium nitrate is going to be soluble. My 2 sodium nitrates are going to dissociate or break apart into 2 sodium ions, AQ, plus 2 nitrate ions, AQ. My second product, my nickel 2 carbonate, I'm going to come back and check my solubility guidelines and see that carbonates are insoluble unless combined with an alkali metal or ammonium. Well, nickel 2 is neither an alkali metal nor is it ammonium, so my nickel 2 carbonate is going to be insoluble, and I'm going to represent that by putting NiCO3 down arrow, letting everyone know that that's a PPT that I've formed. It's insoluble, and it would settle to the bottom of the test tube. We're now at the point in the overall ionic equation where we can circle our spectators. Keeping in mind that spectators are not involved in the reaction, they're going to be exactly the same before the reaction as they are after. They are simply, if you want to think of it this way, watching the reaction occur. I scan through my list and I see, okay, I've got 2 sodium ions that are dissolved as reactants. And when I go after my arrow, look at my products, I have 2 sodium ions that are still dissolved in solution. They are unchanged. They are spectators, and I'm going to circle them. And I work my way across the rest of my reactants that way. So now I come and look at my carbonate. As a reactant in my bottle of sodium carbonate, my carbonate is dissolved in solution. Yet when I look at my product, my nickel 2 carbonate, the carbonate's part of the PPT, it's changed. I would not circle it. It is not a spectator. Same thing's true for the nickel 2 ion. As a reactant, it is in solution. It's dissolved as an ion, but as the product, it's part of the PPT. It was involved. It's not a spectator. But looking at nitrate, I have 2 nitrate ions that are dissolved in solution as a reactant, and the same 2 nitrate ions are still in solution as a product. I've identified my spectators. The next step is to write my net ionic equation. And in the net ionic equation, I rewrite the overall ionic equation, but I leave out the spectators because they're not really involved in the reaction. So I've got my carbonate ion, which was dissolved in solution, is going to combine with my nickel 2 ion, which was dissolved in solution, and it's going to form my PPT nickel 2 carbonate, which settles to the bottom of the test tube. The final step, I'm actually going to have to erase the board to represent. And when you look at your PPT chart, you see in that final box, what you've got is an image that looks supposed to be like the cross-section or a side view, if you will, of what's going to occur in the spot plate. So I'm just going to draw the image up here, and now I'm going to show you the actual demonstration. And in the demonstration, I'm going to take, I think it's 10 drops from the larger bottle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to add 1 drop from the smaller bottle and see what happens. And what I see, and I'm sure you can't see it very well on the camera, which is why I encourage you to run the lab and see it in the spot plate, is I formed a PPT in the center. Well, that's no surprise. When I look at my image here, I actually see a representation of some water molecules that are kind of hovering around here or attracted to an ion on the left. And then I've got water molecules that are oriented the opposite direction, notice, here on the right. And then below that, I have a line showing you the thin section on the bottom. And if you, again, if you could zoom in and see the well, you'd notice that the PPT has in fact settled to the bottom. So I come back down here to my reaction. I identify, as the lab tells you, that the PPT is to be represented along the bottom of the well. And then up on top, we're going to show the ions that stay in solution or that are in solution at the end of the lab. Well, keeping in mind the polarity of water, knowing that the oxygen is more electronegative than the hydrogen, my slightly negative end of the water molecule is actually pointing away from this ion. It's the positive side of the water molecule that is facing this. Therefore, this must be the negative ion. Well, as I look at my products, who are my negative ions in the solution? They're my nitrates. So this must be my nitrate ion that is in this circle. Well, when you look at this arrangement of water molecules on this side, you'll see that it's the more negative side of the water molecule that is attracted to or drawn to this ion, means that this ion must be the cation. I look back at my reaction here and I see that it is in fact my sodium ions, which are the positive ions that remained in solution the whole time. My spectators remain in solution and my PPT settles to the bottom of the tube. If you have any questions, please don't hesitate to ask your instructor, because Mr. Stola has knowledge of chemistry. Hope things go well. You have Thursday and Friday to work on the lab. Bye.